Wow. Thank you so much, and welcome. Thank you all for coming. It's nice to see so many people here. Also, it's a bit intimidating. So my name is Gustav Andersson. I'm senior software dev at Elk Audio in Stockholm. Just a little 1-minute plug for what we do at Elk Audio. We do the Elk Audio OS, which is a Linux-based operating system for musical instruments with amazing real-time performance, with all the benefits of a normal Linux distribution. It runs on a number of platforms, and it's open source, and you can check it out on GitHub. We also do Elk Live, which is a music collaboration tool that allows musicians to play with each other live over the internet with extremely low latency. And you can say that low latency is kind of what we do at Elk Audio. It's currently in a free beta that is Mac only, Windows version coming. You can check it out at elk.live. At Elk, I work mainly in C++ on audio engine parts, meaning real-time, high-performance stuff usually. I'm also into guitars, synthesizers, everything that makes weird sounds. I'm also an occasional plugin maker. So for the next 40 minutes or so, I will be talking about how to make your audio DSP code run faster with the help of your computer. So when you're new to audio development, you try to read up on how to optimize your code. It's easy to get the impression that if you read books and online forums that this is about counting multiplications and divisions, you get the least amount of instructions, and then you want to use vector instructions, that you quickly learn that that is like the holy grail of optimizing. It should be vectorized, then it'll be fast. And to use those, well, you have to write compile intrinsics, inline assembly. You should probably find a library to get away from the platform-specific parts. And you think, that's really, really hard. And it is really hard. Like, I don't know how to write vector intrinsics or inline assembly. And it requires pretty deep knowledge about how CPUs and compilers work internally. And you do all that work, and your code that started out looking something like this, now looks like this. And my main sort of direction of philosophy in code, in this talk and when I write code, is that code is written primarily by humans for humans. So clarity and readability should be a first priority. But it should also express our intent in a way so that the compiler understands it and can compile it in a way that is the most efficient and fastest possible way, which might not be how we would write it. So ideally, we should never have to sacrifice readability for performance. Maybe that's not always true, but maybe 9 times out of 10 it can be true. I like the term collapsing abstractions. I heard it in a talk video by Chandler Carruth. Like, we all use all these abstractions to sort of make sense of the code. Like, loops are abstractions, functions are abstractions, classes are abstractions. But when compiling, they should all just collapse. They should disappear and not be in the way of the compiler, because the compiler doesn't need a helper function. It doesn't need intermediate variables with good names. And I'm absolutely not an expert. I know there are plenty of people in this room who know a lot more than I do about optimizations and compilers and assembly and things. So please be nice to me if I say something that's not entirely correct. But I have spent a number of years trying to write C++ code that is both performant and readable. And I have spent considerable time trying to not write intrinsic, but instead read readable and portable code, but also code that the compiler can efficiently unroll and vectorize and make as fast as possible. And I want to share some stuff that I've learned along the way. And I also am not here to say that hand optimizing code is useless. It certainly has its place, though. What I'm saying is that I think sometimes we underestimate just how good compilers are at optimizing and how much we can leverage that and get pretty far without doing everything manually. So this is, I will cover the intro. This is where we are right now. I will go a little bit on what we mean by performance, very brief on what compilers do to make that code go faster, and then we'll look into some techniques you can use, a few more detailed case studies where there will be a bit of code. I'll wrap up with a summary, and hopefully I will have time for questions. And if you find something interesting, you think I'm wrong on something, just grab me afterwards. I'd love to talk about this stuff over a coffee or a beer later. And there will be a fair amount of code. Also, to get the best out of this talk, I think it's good if you have a reasonably vague idea with things like caches or CPU pipelines or cache prediction, things like that. are and how they impact performance. And there will also be some assembly code, but rest assured, I suck at assembly. I can barely read it, not write it. Probably a lot of people that do here, but I think the reason why a lot of you people came here is because you don't know assembly and you were hoping that you could avoid learning it. And that's also what I've been hoping for. So let's dive in. And the scope here is optimizing like small blocks of audio DSP code. Like it could be an oscillator, it could be 32 samples of a filter or a gain control, but not all of your plugin code, not the GUI code or the non-real-time code. So in the general case, fast means we want the average case to be as fast as possible. We run the code 1,000,000 times, we measure how long it takes, and then we divide by the number of times we ran it. But in DSP code, we also have other constraints. And it was really interesting to see Fabian Renjard's talk this morning, where he looked at the performance of lock-free data structures versus mutexes. And the average case for mutexes was actually a lot faster, but also the worst case for mutexes were a lot worse. Basically, a kind of amortized complexity where you trade a few expensive operations sometimes for a fast average case. But in DSP, we can't have that. We need to have also a fast worst case. And ideally, we want it to be branchless because branches can be expensive, they can be mispredicted, and they introduce a dependency on the data. And also the usual real-time requirements of no locks, allocations, and so on. But this has been covered in a number of previous talks at ADC. But if all of that is true, then we kind of can expect deterministic performance, and we can take our little modules and we can put them in a micro-benchmarking framework, which is, I mean, you can compare it to unit testing. Like in unit testing, we take a block of code, we put it in a fixture, and we test that it conforms to our specifications. But in this case, we take it and we run it in isolation so we can benchmark the performance on it. And this sounds quite simple, but I wouldn't recommend writing it yourself because the devil is in the implementation details. So I would suggest using a benchmarking framework. I've used Google Benchmark, but there's a few others you can use as well. Also asking the compiler is pretty good. If you ask it for it, you can get quite good information. There are some compiler flags you can use where the compiler will output a lot of information about what decisions it makes and if it can optimize something or if it cannot optimizing. I don't know, my experience with MSVC is limited, so I didn't know, I couldn't find any info on that. But if someone has info, they can tell me later. But if you run with GCC, like you shouldn't run it on a large code base because then you get thousands of lines of code, but it looks something like this. And we don't need to go into detail, but you can see that it dumps some sort of cost analysis of what a scalar loop would do or a vector loop. And you can see that the vector loop has the lowest cost, so it will vectorize the loop if it can, because it thinks it's the most efficient. Compiler Explorer also deserves a mention. I think it's an amazing tool. I first saw it used some ADC talk, I think, some years ago. But it's so powerful. It's basically a web page. You put your code there, and then you can select from like hundreds of different compilers, all the common ones and all versions with a number of different platforms. And it shows you what the resulting assembly code will be. And you can pair it with the compiler switches that we saw on the previous slide also. It makes it even more powerful. And then you say, isn't the compiler outputting assembly instructions? I don't know assembly, but you don't need to know assembly to get a lot out of it. And it also has a lot of documentation. You can hover over the mouse and it will tell you what the instructions do. Use it, it's super powerful. Just a little note on why your code might be slow. It could be slow for a million reasons, like conflicting multi-threading, bad choice of algorithms with the wrong complexity. But if we narrow it down to like the small DSP modules or loops over a block of samples that we're talking about here, I mean, you can usually limit it down to a few cases. And I think CPU bound and memory bound are pretty well-known cases. But I'd like to spend a minute on a more complex case. And when I was doing the background research for this talk, I realized that pipeline bound was actually not a widely used term. But I think it's a useful term because it describes a situation where I think technically you're kind of CPU bound because you're limited by the CPU, but you're really limited because you have a long chain of calculations where each calculation depends on the result of the previous one. And the compiler is not able to find other instructions that it can interleave to get better pipeline throughput. And the reason for this is that modern CPUs are heavily pipelined. So even if they can spit out one instruction every clock cycle, it takes maybe 10, 15 cycles for an instruction to finish. So if every instruction depends on the previous one, there will be a lot of waiting for them to finish. And this is something that affects recursive algorithms a lot because they have this data dependency. And we have a lot of DSP algorithms that are recursive. And this is something that the compiler is often not able to optimize efficiently. But it could be faster if we could somehow break up these dependencies, or if we could parallelize along a different dimension or something. Yeah. So a little bit on what compilers do. They do a lot. But essentially, it's about collapsing those abstractions, breaking it down to the most sort of efficient representation of the data. The abstractions are good for us, but we can remove it when compiling. So a crucial thing they do is inline. I don't think I need to explain what inlining is, but I want to mention that the benefit of inlining is not just about removing the overhead of a function call, which is pushing all the registers to the stack and jumping and risking a cache miss. It's maybe more crucially, it's about getting more context about the arguments that you're calling the function to or where it's used. Say that you're calling a function with a constant. And if you inline the function, well, the compiler knows about this, and it can maybe optimize the function a lot more because it knows that certain things are constants. And compilers do a lot of heuristics to determine when and when not to inline functions. And they're generally pretty good at this. So you should not consider not writing a function just for the fear that it won't be inline and it will hurt performance, because if it can be inline, it most certainly will. Another very important thing they do, and maybe the most important thing in our case, is optimizing loops. Because loops have this inherent branch in them, because there's either a loop counter or there's some condition you need to check every time. And there's some penalty for checking that condition, and it can also be the branch can be mispredicted. So as with functions, sometimes if the loop count is known, the compiler can just remove the loop and take the body of the loop and just copy it that many times. Sometimes it cannot unroll the loop fully, but it can unroll it partially and do some sort of widening and interleaving, where you can do multiple iterations in one to reduce the overhead of the loop. It can split loops if there's control flow in the loop. Compilers are also good at detecting if some statements are not updated in the loop, or they're always calculated to the same value, and then it can just pull them out of the loop because they don't need to be updated every time. A little bit on the vector instructions. Like we think that this is often the holy grail. We wanted to vectorize it. But as the name suggests, they're a way to sort of work on multiple data at the same time. Like if you can't go faster, you can do more with the same instruction. And since we're using, in audio, we work on blocks of samples at a time often. So then we think, oh, this is very good. We can work on multiple samples at a time. So the way they work is they use special registers that are wider than the normal CPU registers. Like for SSC, these are 128-bit wide, and for AVX, it's 256. So in the 256 bits, you can fit either 8 32-bit floats or 4 64-bit doubles. And then you can multiply it with another 256-bit register. And ideally, that means you could apply a gain to 8 samples at a time in one instruction. And compilers are usually good at vectorizing data that doesn't have dependencies. Things like multiplying a gain value or FIR filters. That kind of thing usually can be auto-vectorized quite quickly. Even non-fixed size loops will be vectorized often. And the way they do it is they do some sort of preamble at the beginning of the loop where they go with like one sample at a time until you get to a boundary of like 4 or 8 samples or whatever the current SIMD width is. And then it will do like 4 or 8 or 16 at a time. But unfortunately, compilers have a really hard time vectorizing data if there are dependencies. Also, if you compare with any level of optimization above, you should not count on the compiler to execute the statements in the order you wrote them, because the compiler will rearrange things so that it thinks it gets the best pipeline throughput. It will remove variables that are not needed. It will try to reduce algebraic expressions down to the simplest form. The exception here is atomics, and I think also Fabian gave a really good walkthrough of how atomics use and the memory ordering of atomics use. But basically, atomics allow you to specify how much or how little the compiler can reorder your code. I want to show a little bit of an example here. This is just a function that gets a value in an array, and the value is a fractional value, so it does linear interpolation. And these functions they're the same function. It's just the top one is written with a number of intermediate variables just to make it more expressive and portable, and the bottom one is written in like the most compact way I could imagine. But if you look at the resulting assembly code from this, it's exactly the same. Like all these intermediate variables, they just disappear. And I think it's actually interesting that the bottom one, it actually has 3 memory addresses. Like you read d of f 2 times, and you read d of f plus 1 once. But obviously the compiler understands that. We don't need to explicitly read that and put it in an intermediate variable. That was a bit of context. Now we're getting to some interesting stuff. So how do we nudge the compiler in the right direction? So we look at how to promote auto-vectorization, how to make inlining happen, and some notes on floats and constants. So ideally, if you have a tight loop over a block of samples for a filter or an oscillator, what you want is that you want the compiler to fully unroll the loop, and you want it to vectorize. And to do that, there's 2 things that you should do to give the compiler the best chance of doing that, and that's the loop count should be known to the compiler at compile time, and there should be no control flow in the loop. So no early exits, no sort of jumping to the function if some condition is true, but just loop through the whole thing. And on that topic, tomorrow, my colleague Elias Bergström will do a talk on the architecture of DFWs. It's a super interesting topic. You should really go see it. But in that context, I'd like to say that when we built Sushi, which is the DAW in Elk Audio OS, one of the sort of key architecture decisions that we took early on was that it should run with a fixed buffer size, just to give the compiler the maximum amount of headroom and space to optimize. And that's a good thing to do in DSP. But if you try to do that in an audio plugin, a Juice plugin, VST plugin, you'll quickly realize that the APIs of all the plugin APIs out there, they don't support this. The only information you can get from the host is the maximum number of samples. Like the host can say, I will call you with 256 samples, maximum. But then you don't get any information. It could call you with 1 sample or 2 samples or 15 samples. Unfortunately, then if you do your plugin with a fixed buffer size, you need to buffer, and you need to tell the host, well, I'm buffering, so I'm delaying the input by this many samples. Unfortunately, it would be nice if in the future we could have plugin APIs where you can have a bit more detailed communication between the host and the plugin, so the plugin can say that, yeah, I would prefer if you would always give me blocks that are multiples of 32 samples or something like that. But until that's the case, you would need to buffer if you do a plugin with a fixed buffer size. Another example, this is a function Again, there's two versions of the same function. They're identical. What they do is they multiply an audio buffer with a gain value. And the only difference is one takes a stud array, and the other takes a stud vector. So the stud array is a fixed size container, and the stud vector is a dynamic container. Another version looks like this, and this doesn't do a constant gain, but it does a fade. So you set a start gain and an end gain. So if you benchmark this, you'll quickly see that it's about twice as fast with the stud array than the stud vector. Even though the stud vector is actually, it's partially vectorized and made very efficient, so it's still very fast, but if you have a fixed buffer size, it's going to be even faster. Some note on inlining, and just to make sure that functions can be inlined, there's a keyword that is just a recommendation, and it's largely ignored by the compiler. But you should know that if you put a function definition in a header file, it will almost certainly be inline, especially if it's a member function and you put it in the definition of the class. And this is used a lot by the STL, the standard template library, which is entirely header-based. And if you look at these algorithms, they're quite complex, but because they're inlined, compiler can often optimize them heavily. The other example is if you have a function that's defined in one header file, so one source file, it's in one compilation unit, and you link to it from another compilation unit, then it cannot be inlined unless you use a link time optimization, which I think you should. And virtual functions are very hard to inline because of their double dispatch. You need to go through a vtable, and you don't know at runtime which function you're actually going to call. And they also have a higher head. There's an extra indirection, so it takes the penalty for a virtual function is higher than a normal function. So you should avoid virtual functions like in your inner loop over a block of samples. You can go, there's an article on ISO-CPP with all the dirty details on inlines. Some notes on the kind of traps you can fall into when working with floats. We said you shouldn't count multiplication of divisions, but maybe divisions are worth counting because they're much more expensive than multiplications. And often the compiler can, especially if there are constants, the compiler can optimize this by basically replacing a division with a multiplication. In case you cannot do this, like a common trick is if you have a value that's used a lot and divided by a lot, for instance, like the sample rate that we often store and we divide with it to get a normalized frequency. A common trick is you just store 1 over the sample rates and you multiply with that value. So it'll save you one division. And it's not a lot, but if it's used in a lot of places, it can have a significant impact. Also note that floating point literals, their type are doubles if you don't specify anything else. So we will look at a little bit of an example here. And this is Compiler Explorer. So this is a very simple function. It converts between degrees and radians. And we were hoping that, okay, this should ideally should optimize down to a single multiplication. But it doesn't. So why? And I looked these assembly instructions up, and the VCV to SS2D, it's a double to float conversion. So apparently that's done at runtime. And then there's one multiplication and then one division. So apparently it takes it as we wrote it by multiplying with 180, dividing with pi. So let's first look at the double and float conversion. We can remove these if we make sure that the constants are actually floats and not doubles. So we put an F after the 180, and the pi will make sure the pi is a floating point constant. You can also use const per constants where you can specify the type. So now the double to float conversions disappeared, but we still have one multiplication and one division. Like we were hoping that the compiler would optimize this. And the reason why the compiler doesn't optimize this is because they have this strict IEEE floating point compliance. That basically what we're saying is you take the irradiance, you multiply it by 180, and then you divide the result by pi. And if we were to optimize it, we will actually be saying to the compiler, you should take 180, you should divide it by pi, and the result of that you multiply with the radians, which mathematically is identical, but if you do it in floating point math, it's not exactly identical. Or it will be almost the same, but it will have a different rounding error. And by default, compilers are very strict about this. So what we can do is, well, we change the order of evaluation explicitly. And now we see that, now we get what we wanted, which is we have one constant, which is 57.29, and the function was reduced to a single multiplication. Another way to achieve this, if you compile with fastmath. Fastmath is actually the kind of macro flag that enables several flags, but you disable this strict IEEE conformance. So, a few more case studies. I'll have 3 of them that we will look into. A little bit of it like in getting branchless code, or more like thinking that maybe you already have branchless code. So the benefits of branchless code is that it's more deterministic. Like there's no branches that can be mispredicted. And it doesn't depend on the data. Like you want your DSP to take the same time, regardless if you're passing silence or noise or loud or silent signals. And this is good advice. But I was reading some articles prior to this talk, and sometimes branchless code is misunderstood as it's code that doesn't contain if statements. But that's not true, because often small common operations can be made branchless by the compiler. And this is a very, very simple example that I saw in these articles. Like, the suggestion was that this is code that could be branchy, so it should be rewritten to be branchless. But if we look at what this actually compiles to, it's already branchless. It's one compare, and it's one conditional move instruction. So you could rewrite this with conditionals, which obviously is the same thing. You can also use studmax, which I think you should, because it's probably the most expressive way of writing your code. There was also some suggestion that, oh yeah, you could replace the if version with this, which is a bit mask way of supposedly branchless way of implementing a max function. But it still compiles to the same code. In fact, the only suggestion that didn't compile down to the same code was this, some sort of bit-shifted version, which is kind of hard to read. And it gets even more interesting when we put this in a loop. So we put this in a loop, and we loop over 16 integers and do the max of them. And we get this, which is actually very different from that. There's no conditional move here. And you can see also, because you have this block that kind of repeats, and the RDI, you see that it increases with 16 bytes every time, so it's apparently vectorized. It moves at blocks of 4. But I find it interesting. If we look into, and I looked up these instructions to see what they do, and there's a PCM GTD, it's a compare greater than, and there's a P and N, and the P stands for packed, which means that it works on packed values in a SIMD register. So it works on 4 at a time, and it does bitwise and not, and bitwise or. And actually, if we go back to this suggested bitmask version of max, it looks like, I mean, we have one comparison, and we have one and an or, and an and not. So again, I suck at reading assembly, but if I were to take a guess, my guess is that the compiler outputted a vectorized version of that bitmasked and max instruction. And all we did was we put studmax in a loop. Actually, we put studmax in another function that we didn't designate as inline, but it inlined everything anyway. And it made this, which I think is pretty cool. And if you compile with something for a target that has AVX support, which is like, I think, more or less every Intel CPU the last 15 years, you get this instead, which is, it basically compiles down to one single VP max vector instruction, hardware instruction to do just that. So all that effort into trying to write branchless code when the compiler can very well generate very efficient, optimized branchless code for us. Yeah, and just for wrap up, I benchmarked the bit-shifted max version. It wasn't faster. It was actually slower. So the conclusion, I think, is for these very simple common operations, you should only try to beat the compiler if you have a really good reason to do so, because the compiler kind of works by trying to identify patterns, and if you can identify a pattern, it knows how to implement that in the most efficient way. And you should always, if you do it, you should always profile and you should check what comes out of the compiler, because it could be the same thing, or it could actually be worse. And if you really want to roll your own, before you do that, you should also look into using highly optimized math libraries like Intel IPP and NI10. And there are also some cross-platform alternatives available. And only then should you try to roll your own. Another thing, the fastest data we have is the data that's in registers, and then it's in cache, and then it's in main mem, and everything else that we shouldn't even care about in the audio thread. So one thing I've spent some time trying out is a lot of times our audio code looks a bit like this in a general way. We have a process function that takes a block of samples, and we loop over all the samples. And for every sample, we have a state which we somehow multiply in. And then from the result of that, we update the state, and then we write back the state. And the state is usually a member variable in heap mem somewhere. So my thinking was that maybe we can optimize this by trying to, because my understanding of the C++ threading model is that it can, it doesn't consider multi-threading. It just looks at everything in isolation. So if there are variables updated in the loops with lots of, because you have lots of intermediate writes in this case. For every sample, you write back the updated states, but you don't actually need to. But I've not seen a compiler to actually optimize that away. So my thinking was, well, we explicitly put the state on the stack, also given that the state is, we're assuming that the state is small and it's easy to copy. And then we use that intermediate state, and then after we've done looping over samples, we write it back. So could this reduce the amount of writes to heap mem and make it faster? Just for clarity, I wanted to show you this, and this is the simplest type of lag processor that I could think of. Lag processor meaning something that interpolates between parameter values, because you usually have a sample rate, and then you have some sort of control rate that is lower than the sample rate. So this interpolates between parameter updates that are done at a control rate. And if we put this in a gain control, we get something like a VCA. So it linearly smooths the gain. And then we can apply this idea that I had, that, okay, we put the lag. And the lag was only, if we go back and see, it's only, the state here is only 2 floats. So it should be very cheap to copy to the stack. And then we use that, and then we write it back. And then we try to benchmark this. I don't show you the full code because it's just too much, but I did this with a state variable filter implementation, and I did this with the VCA that we saw. And with the filter, we get maybe 20% improvement. But with the VCA, it was, wow, a lot. It went from about 200 nanoseconds down to 24. It's like, so what happened? And now this is going to be a bit messy, but I've tried to sort of highlight with different colors to see what points where. And the output of GCC, if this is the first case that apparently failed to vectorize, because it says missed, not vectorized. And it says complicated access pattern that points to this return value, the get function in the lag generator. While the version with a specific, with an explicit state on the stack, it did it. It optimized it. And it says optimized loop vectorized using 32-byte vectors. So apparently the difference in speed is because this was able to vectorize and the previous was not able to vectorize. But then just last week I went back to this and I was trying to like, why didn't it vectorize? I was actually able to make it vectorize again and again. I see a parallel to Fabian's talk this morning that if I change the signature to look like this, then I was able to make it vectorize without actually putting the state explicitly as a stack local variable. And you notice two changes. One is I pass raw float pointers, not a audio buffer object. And you notice also the restrict keyword. So this kind of gave me a clue to what's happening. Maybe it's not actually that we're reducing heap memory writes. It's more like we're giving the compiler more chances to optimize. And actually, if we go back and look here, the first 3 lines, it says, consider runtime aliasing test between in and out. And that we actually have in the one that did optimize. But then we have lag and step, which are the 2 state variables of the lag generator. And it says consider runtime aliasing test between those variables and the out variable. So apparently I did some sort of aliasing here that prevents the compiler from optimizing. And what is aliasing then? It's not aliasing as in digital audio, but it basically means that you have multiple pointers and they could potentially point to the same data in memory, or you could have arrays in memory and you could maybe access the data of one array through the pointer to another. And often this looks like, but it's pretty far-fetched. But the compiler is not allowed to disregard that. It must write code so that it will work even if there is aliasing. So sometimes this prevents optimization, that it forces the compiler to reload things from memory every time. So then you can use restrict, because if you put a restrict specifier, it means you're telling the compiler that I, as a developer, I guarantee you that there are no other copies of the data. They give you a pointer, and there are no other pointers that points to this data. And then the compiler says, sure, I can optimize more. Unfortunately, restrict is a keyword in C, not in C++. There is a few compiler extensions in most common compilers that works more or less the same. There was also a proposal to add something like this to C++. I don't know the update on that. It was last updated in 2015, so maybe it's not. And the other downside is you need to use raw pointers if you need restrict. So I'm sort of on the fence. I don't really know what my recommendations are. So I'll leave it here, and you can use it if you want. But as I've seen, there are other ways also you can get around this. But it would actually be nice if we had some sort of restrict-like semantics in C++. My final point is on going back to something I've mentioned a couple of times in the talk, that we have these recursive algorithms in DSP a lot, like all our IIR filters, all the stateful things where we update the state every time. We have where f of n is a function of the previous values. And this is very difficult for a compiler to optimize. One, because it often introduces pipeline dependency, so the pipeline throughput will be low, and it's also very difficult for the compiler to vectorize this because of these dependencies. So what can you do? Well, one thing you can do is you can try to identify multiple filters that run in parallel. If they have parallel audio graphs, like you have multiple voices of a synthesizer, or you're doing stereo processing, you can go something like, well, instead of the top version where you calculate all the samples of one filter in series and then all the samples of the other filter, maybe just interleave them. Like one sample from this filter, one sample from this filter. And when you get back to the second sample, like all the previous calculations have gone through the pipeline, so you can just keep going right away. So I did this with some template magic and benchmarked it. And actually, I benchmarked on this machine, which is like, it's a 7-year-old i7. So here the cutoff point seems to be around 4 parallel filters in general that I can do at the same time. So basically, you can do 2 filters basically for free, and 4 filters almost for free. In fact, in Clang, it's actually surprising that 2 filters are more faster than using 1 filter. But I don't know why. I haven't looked at the code, actually. But this is only applicable if you have if you have multiple audio paths, like you have multiple voices, or you're doing some multiple stereo processing. And sometimes you just have one audio path in mono. What do you do? Well, sometimes I think maybe for EQs you can do, if you EQs with multiple bands, you can maybe split and do the bands in parallel and do a mix down. I haven't tried it, but it might be efficient. But if you have a filter with a higher order filter with cascaded second order sections, you can actually, if you put a 1 sample delay between the stages, now they're actually independent, and you can go back and do this, like you do 1 sample from the first one, 1 sample from the second one, etc. The downside is, of course, if you have 4 sections, 8 order filter, you have 3 samples of delay. So you delay the whole output by 3 samples. But I benchmarked this, and again, it seems like it gives you about the same performance, like pipelining filters like this. It was pretty cool. I've actually used this for an anti-aliasing filter, and then the delay is not so much a concern anymore, because if you do it in 4 times oversampled, when you then downsample, that delay of 3 samples is just less than 1 sample at the end. So that's something you can think about. But to do that, you need to rewrite your architecture. The compiler cannot do things like that on its own. Like basically finding another vector dimension for the compiler to parallelize along. Yeah. So just to wrap this up, a few pointers on things you can do to help the compiler optimizing your code. Like, you should ideally use a fixed buffer size, because that will give the compiler a lot more room to optimize and vectorize. Make sure that all the functions you call in, like your inner loop, can be inlined. Write branchless code, but branchless code might not actually be what you mean. Sometimes it already is branchless. Try to exploit this kind of parallelism for recursive filters. You can try explicitly keeping state variables on the stack, or you can go for a more restrict-like semantics. You should benchmark the standard library functions. Because usually all the small ones, the min, max, clamp, fill, they usually compile down to something really efficient. While the more complex ones, like std sort or std min, max element or something, they might be slower than something more optimized. And also try to minimize floating point division by using all the tricks that we saw to make that transition happen. Some more material that might be interesting to read. Compiler Explorer. Agner Fogg's homepage is a really great resource for everything that optimized related. There's actually a 2-part series that on our webpage that I wrote a couple of years ago on using std algorithm in audio part. It's quite interesting. There's also a few some CVP and ADC talks. I think that was it. Thank you for listening. Questions?